the interactions of volcanoes with the atmosphere, with the hydrosphere, with the biosphere, with the lithosphere. Volcanoes are incredibly important for pretty much every single geosystem we have. So here's the lecture outline I'm going to talk about. So, like I said, interactions of volcanoes with other geosystems, why they're important, why they have proved important, why it's important to study them. Global patterns of volcanism. We've already covered this, to be honest, when we looked at plate tectonics, but I'll introduce a nice little summary. And I'll talk to you a little bit about volcanic hazards and what we mean by that term volcanic hazard, and how it doesn't just relate to volcanic eruptions, there's a lot of things associated with volcanoes, and also some benefits. And finally, if we have time, I'll introduce earthquakes, which will be the main topic of tomorrow's lecture. So we're really talking about geohazards in the next 2 lectures. So some crazy geologists, back in the day, I talked to you last lecture about the Russian geologists who sailed down a lava flow on a raft of solidified lava, which was 300 degrees, and they had to keep standing in their asbestos boots. Well, the whole point of them doing that was to measure the temperature of the lava flow and to measure the gases emitted by that lava flow by volcanoes. And people have got incredibly close to volcanoes in order to measure what's coming out of them. And what we find when we measure those volcanic gases is that most of them are made of water. So 70 to 95% of those volcanic gases that come out of a volcano are water vapor. Now, where does that water come from? So a lot of that water is water that's never met the surface of the earth before. It's trapped underground, deep in the earth. It's one of what we call a volatile. And then when that magma is erupted, when those gases are erupted in the volcano, they meet the atmosphere for the first time. Other water molecules that come out of volcanoes are actually groundwater or other kinds of meteoric water that is underground. It gets heated up by magma, and then it comes to the surface as steam. The rest of the components of volcanic gases, we get a broad mixture, but there's a lot of CO2 in there. There's a lot of carbon dioxide. This is why volcanoes are important in times in the past. So there have been times in the past when we've had a lot of volcanic activity on land. We're talking huge areas of the earth covered with volcanoes. And at those times, quite often we see incredibly hot climates. So a lot of people have suggested that the increased CO2 input from volcanic activity caused those ancient greenhouse climates. And then other gases we see, we've got sulfur dioxide, it's a very common volcanic gas, SRSO2, and various components of nitrogen, hydrogen, carbon monoxide, sulfur, chlorine gas. These all come out of the volcano when it erupts, or not even when it erupts lava. They're constantly coming out of the sides of volcanoes or in volcanic regions. And this is really important for the evolution of the Earth. Very early Earth didn't have oceans, and now obviously oceans cover most of the Earth's crust. So one of the biggest debates in Earth evolution is where that water came from. It's thought that some of that water would have come from outer space, because a lot of comets, they have a lot of ice on them, and there was a high amount of impacts, a large number of impacts on the Earth early in its history, and it's thought those meteorites and etc. brought lots and lots of water to the Earth. But a lot of it, the general consensus is that most of it came from inside the Earth. So when that early Earth was very hot, the dense materials sank and formed the core, and a lot of those volatiles, the sulfur, the carbon dioxide, the water, were emitted out into the atmosphere through volcanoes. And obviously when the early Earth was very hot, that water remained in vapor state, or in gaseous state in the atmosphere. But as the Earth cooled, it's thought that that water vapor then condensed and formed what we now have as the oceans, along with some components from the rest of the solar system. And of course the atmosphere, the early atmosphere was dominated by these materials, these molecules which came out of volcanoes. It wasn't until we started getting organisms that could take up that CO2 from the water and produce oxygen that we really started seeing a build-up of oxygen in our atmosphere. Oxygen is not a gas that commonly comes out of volcanoes. So these are the important gases that come out of volcanoes. So just to talk a little more about the hydrosphere, so anything to do with water on or near the Earth's surface. I've told you a lot of water vapor is released from volcanoes, and actually even volcanoes that we call extinct, like much of Fiji, there's still a lot of water underground being released by that underground magma chamber that's now very old. And also there's a lot of groundwater being heated by the residual heat from those volcanoes. So water is a really, really important component of the volcanic system. And the water that surrounds any volcanic area is very hot, it gets heated up. As I've told you before, hot water can dissolve minerals from the surrounding rock. And so these hydrothermal fluids, we call them, hydro means water, thermal means hot. They contain a lot of minerals. And they push their way through the Earth's crust, and when they reach the surface, they can express themselves in many ways. They can express themselves as a hot spring, so simply where water comes out of the ground and it's hot. This is an example of a nice little hot spring in Vanuatu on the bottom left-hand side. Now the water reaching the Earth's surface in Vanuatu in many places is 100 degrees or even more because it's superheated underground. We will increase higher temperatures than 100 degrees underground. And this is a picture of a student cooking in the stones of a hot spring, so you can't sit in that hot spring, it's too hot. In other places they're at lower temperatures. When that water reaches the Earth's surface in the form of steam, we call it a fumarole. And in both of these cases, as these hot springs cool and depressurize, they can precipitate a lot of their minerals. And this is this famous volcano I've shown you lots of pictures of in Indonesia, which that gas that comes out of the volcano is very water-rich and very sulfur-rich. So as it comes out to the Earth's surface, it precipitates pure sulfur on the sides of these fumaroles in large quantities. And so you have these miners who are mining the sulfur on the side of an active volcano, where the pH of any water droplets in the atmosphere is incredibly low. It's acidic because the sulfur molecules coming out of the volcano mix with water in the atmosphere and create acid droplets. So they don't have a very long life expectancy down there. Sometimes when that water reaches the surface, at very high pressures, it can form these spectacular features called geysers. This is a famous example of a geyser in Yellowstone National Park in the USA. So we have this big magma chamber underground in an old caldera. It's heating up groundwater. It's releasing its own water from the magma. Pressure builds up underground, and you've got all these gases and water vapors emitting. In this case, it erupts to the surface roughly every 65 minutes. So every hour, you can go and see Old Faithful. They call it Old Faithful because it faithfully erupts every hour. And so you can go and wait for it. And sometimes it shoots as high as 60 meters into the air. This hydrothermal fluid is also incredibly important for generating electricity in certain parts of the world. It's a really nice, neat example of humans using nature, not destroying it, to produce electricity and things that modern society needs. And this is a nice geothermal plant in Iceland. So Iceland in the North Atlantic pretty much has all its electricity coming from geothermal energy. And so basically, steam and hot water is pumped up to the surface, so that it's naturally heated under the ground because it's volcanic. It's pumped to the surface, it's put into a giant turbine. So you have this turbine that's being pushed by the steam pressure, and then that motion of the turbine generates electricity, and then the water is, as it's cooled, it's pumped down to the ground where it's heated up again, and the whole thing is self-sustaining. This is also really common in New Zealand, and a colleague of mine, Holger Summer, who presented last week in your lecture at the same time, he is, along with me and a few others, trying to set up this in Vanuatu, or at least see if it's feasible. So it'll be a way of Fiji generating its own electricity. So also volcanism is pretty important for the atmosphere. As I've told you, a lot of the gases in the atmosphere are gases that have been emitted by volcanic activity. Now on Earth, because we have life, we've altered the composition of our atmosphere just because of life, respiration, photosynthesis, now the burning of fossil fuels. The rest of those gases have mostly come from volcanic activity sometime in the past. And also just on modern day scales, volcanoes, if they're explosive, will release a lot of ash. They'll also release a lot of gas which can dissolve in tiny water droplets. So when we get gases dissolving in tiny water droplets, we call them aerosols. And both the ash and the aerosols can actually block sunlight from hitting the Earth. And actually, if the eruption's big enough, and there's a big enough ash cloud, that can cause climatic cooling on year scales or even multi-year scales. And there's been a few examples of that. So in 1992, maybe it's even 1991, I'm not sure, Mount Pinatubo in the Philippines erupted. And there was a huge ash cloud. This is just in the early stages of the eruption. It grew bigger and bigger and bigger, went high into the atmosphere, and it actually reached around the globe. And it caused, over that year, in 1992, an average of 0.5 degree cooling, which doesn't sound like much, but it's quite a lot on a global scale. And an even larger example was the eruption of Tambora, which is in Indonesia. This is the eruption I talked about the other day, which was absolutely enormous. They think it must have been the loudest sound anyone has ever heard on Earth in human history, because people heard it 5,000 kilometers away. It was an enormous eruption. It was a phreatic eruption where magma rising heats up lake water and seawater, creating this incredibly explosive eruption that destroyed an island. Oh, this is anyway. Oh, this is an incredibly huge eruption, and they talk about in literature in Northern Europe the year without a summer, and it corresponds to this year. So even though this is over this side of the world, the ash cloud covered the globe so much that it caused climatic cooling over a several-year period, even in Europe. And poets wrote about it being the year without a summer. And on the flip side, I talked about climatic cooling. I also talked earlier about climatic warming. Intervals in the past that have had huge amounts of volcanic activity, releasing CO2 to the atmosphere, have been linked to these greenhouse climates. There are many, many ways in which volcanoes can address climate on very different timescales. So just to summarize, if you like, global patterns of where volcanoes sit. So by far and away, most volcanoes sit around this Pacific Ring of Fire. So we're here, we're sitting in the Ring of Fire, we're just off it, about that basin. And actually 80% of these vent volcanoes, so not the fissure volcanoes, these vent volcanoes, occur at subduction zones. So where you have one plate subducting under the other, fluid-induced melting and volcanic activity, and that's exactly why we get so many volcanoes around the Pacific, because all of these volcanoes sit on subduction zones. We can also get some vent volcanoes at divergent plate boundaries, but these tend to be these fissure-type volcanic eruptions, so narrow cracks in the Earth crust, where the plates are being pulled apart, magma rising, and you have sheet-like volcanoes rather than these central vent volcanoes. And I also talked about before the fact that we have these anomalies, these volcanoes sitting in the middle of plates, nothing to do with plate boundaries, and they're formed by these mantle plumes. So these anomalously hot parts of the mantle at the core mantle boundary rise up through the mantle, meet the Earth's crust, and through decompression melting, form these volcanoes, which sit above what we call hotspots, all these hotspot volcanoes. Just to go through those different situations in a little bit more detail, but not too much. So I'll start where plates are pulled apart. So predominantly mid-ocean ridges. This is where two oceanic plates are being pulled apart. The mantle is rising underneath because it's hot. As it loses pressure, the melting temperature goes down and it starts to partially melt. And the rock that it partially melts is the top of the mantle in a layer called the asthenosphere, which is that slightly more fluid, more ductile part of the upper mantle. The droplets rise, form a magma chamber, and eventually erupt to the Earth's surface and form new oceanic crust. And then those plates are pulled apart and the process repeats. Because the crust is quite thin here, that magma hasn't got far to travel from where it melts, so you tend to produce basalt here because it hasn't had a chance to fractionally crystallize or differentiate. Okay, so we tend to get mainly basaltic magmas here, lavas here, so they're not very explosive. Because remember, basaltic lava is not very viscous, so it runs away quite easily. And these are obviously really, really important plate boundaries. So the oceans cover most of the Earth, 70.1% of the Earth, and that ocean floor is entirely made of rock, apart from the sediments on top, produced by this plate separation. So the entire ocean floor has been produced in the last 200 million years. That's how much lava is produced every year at these boundaries. Yeah, in the last 200 million years, the entire ocean floor has been produced. The oldest ocean crust we see is 200 million years old. And it's all produced by these fissure volcanoes at mid-ocean ridges. And this is a nice diagram of the mid-ocean ridge. Again, we've got decompression melting, mantle is rising, it's depressurizing, it starts to melt. And either it solidifies underground as gabbro, or it solidifies as dikes, or it reaches the surface and solidifies as pillow lavas. And there's something crazy like 10 cubic kilometers of this lava is produced every year, which is a huge, huge amount. It's incredibly important, these boundaries are incredibly important for the lithosphere, they're producing lithosphere. They're also really important for releasing chemicals into the oceans. So ocean chemistry is strongly linked to the chemicals that come out of mid-ocean ridges. So obviously some molecules and ions are washed from land, but a lot are coming into the oceans. They're incredibly important for ocean biology. End of the 1970s, when we first sent cameras down to mid-ocean ridges, we found these incredible vents called black smokers. And this is where seawater circulating through the crust of mid-ocean ridges. I know I've shown you this diagram loads of times. It's dissolving minerals as it heats up. It rises as it heats up because it's less dense. And it comes out on the surface, on the seabed. And as it hits the sea floor, the seawater, it cools and minerals start to precipitate in tiny, tiny particles, mainly sulfide minerals. And we didn't discover until around 1980 these incredibly diverse communities of tuberums, of crabs, of bacteria that live off the sulfides. They don't live off oxygen or carbon dioxide and sunlight, so they're chemosynthetic ecosystems. And the current theory is, or not a theory, idea, hypothesis, is that this could have been where life began, because in a primitive Earth, we had no oxygen on land, we had no evidence of creatures on land. We know that life started in the ocean. How did it start? This is a very concentrated area of heat, with lots of chemicals in it, lots of water. Maybe ancient communities started here. That's one of the things that's being investigated, whether you can generate life just by pumping these chemicals out of the ocean in a very hot manner. And this hydrothermal circulation is incredibly important, as I said, for ocean chemistry as well. And I really like this statistic. In about 10 million years, which I hope you realise now is not that long in terms of geological time, the entire volume of the ocean is circulated through crust. Oh, and if you haven't seen the Facebook page, it's a really nice, this YouTube video is a really nice GIF showing the production of pillow lavas. Can't picture it, it's quite good. So moving on now to where you have one plate subducting under the other, so convergent boundaries. So either where one oceanic plate is subducting under another oceanic plate. This is where we tend to get our nice vent volcanoes. So as one crust subducts, it's pushed deeper down into the earth. The water from that wet oceanic crust is now squeezed up. It It lowers the melting temperature of the mantle above. You get droplets of magma forming that rises up through the crust. The crust is slightly thicker here as it builds up because we've got compression, mountain building, volcanic activity building up. So in the later stages of subduction, that magma that's rising tends to undergo differentiation. So you can imagine in the magma chamber that early formed crystals sink. They're effectively removed from that magma, making it more felsic. That magma rises, early formed crystals sink. It becomes more felsic and silica-rich. And also it can dissolve parts of the crust it's rising through, and that changes the composition of the magma. So what we can see at these subduction zones is not only basalt, we can also see andesites and sometimes even rhyolites, so felsic lavas. And where we have an oceanic plate subducting under a continental plate, that magma that's rising has a much further distance to go. Also being transported through silica-rich, buoyant, light continental crust. So when it dissolves melts part of the continental crust and mixes its chemistry, it becomes a lot more silica-rich. So you tend to have more andesites and more rhyolites, and therefore more explosive eruptions. As I told you last week, that if you have these viscous lavas, like andesites and rhyolites, coming close to the Earth's surface, because they move so slowly because they're viscous, imagine that squeeze with tube of old toothpaste being squeezed. It doesn't run out freely, it will be squeezed up into the Earth's surface, pressure from gases and water builds up underneath that plug, and eventually it blows. And you get these really nice, spectacular volcanic eruptions, such as this one, which is a recent eruption in Patagonia. And there was a really nice image on the Facebook page, which I liked, and yesterday they confessed they faked it. But it was based on footage of a lava, because it was a lightning storm basically in this volcano. They'd taken lightning footage from an earlier eruption that they didn't get as nice videos from, and then they superimposed. So technically it could have been true, but anyway, the BBC faked it. But this is a really nice explosive eruption in the Andes of South America, which sits on a convergent boundary between continental crust and oceanic crust. And this is a volcano like that. It would have formed because we've got fluid-induced melting, rising up, forming magma chambers, differentiating, building up here, and eventually erupting. So fluid-induced melting occurs at subduction zones and tends to produce the water explosive. Not always in young island arc, by the way. You don't really get that explosive volcanoes in very young island arcs, but it's especially where we have either old oceanic island arcs or continental margins where you have subduction. I also talked before about where we don't have volcanism at the edge of the plate, we have it in the middle of the plate. We talked about hotspots, and these are also usually basalt because they form an oceanic crust. Where they form an oceanic crust, they tend to be basaltic. The oceanic crust is thin. That mantle plume is rising through the Earth's crust. It's buoyant and it's hot. Decompresses, causes partial melting in the upper mantle. That magma rises through and erupts, but it hasn't had far to travel. It doesn't really differentiate that much, so it produces basalts at the Earth's surface. However, where they come under continental crust, that's where you get danger, like the Yellowstone caldera, the Yellowstone hotspot. Because continental crust is thicker, you can start differentiating the magma more as it rises through the crust. It incorporates the silica-rich crust in it, and you get these really violent eruptions. But they're all formed from decompression melting. And this was the example I gave when I talked about plate tectonics of Hawaii. So the southeast part of the Hawaii volcanic island chain is active. Whereas if you move northwest, the volcanoes get less and less active, and these are all extinct here. And that's simply because you get volcanic activity where you sit above a hotspot. A hotspot is fixed in place in the Earth, but obviously the plates are moving over the hotspot. So as the Pacific plate moves away from the hotspot, those volcanoes become extinct, and new volcanoes form. So the current active area of the Hawaiian island chain is here, the southeast side. All of these are extinct. These all once sat over this hotspot. And I also remember telling you last time about large igneous provinces. This is where we have fissure volcanoes that in the past have erupted huge volumes of magma and lava. This is a map of the Earth showing places where we have huge thicknesses of crust because of these incredibly voluminous volcanic eruptions in the past. There's the Java Plateau I've talked about before, where the ocean crust is actually about 30 kilometers thick instead of 7 to 10 because of these huge piles of lava that once erupted several hundred million years ago. And it's actually believed that these were formed from a young mantle plume. So as you have this heat anomaly at the core mantle boundary, that heat starts to rise, the hot mantle starts to rise, and what we believe is still in the hypothesis stage. When it first meets the crust, it's incredibly hot, produces incredibly large amounts of plasma, and that forms these flood vessels. And then as it dies down a little, that's when we just simply get our hotspot volcanoes. But there is some evidence that this doesn't quite work. But anyway, that's the current. So just to talk about humans for a little while, volcanoes are incredibly good for us in some ways. Lots of civilizations have based themselves on the feet of volcanoes, either for religious reasons, but mainly because the soil is incredibly fertile via volcanoes. But they can form hazards to humans, to wildlife, and there's the obvious hazard, which is getting covered with lava, or getting hit by a volcanic bomb, or getting buried in volcanic ash. These are all quite obvious ones. The less obvious ones, I suppose, are things like the lake paths. So these mud flows where we have volcanic material mixed with water, maybe melted snow or a river, and they become incredibly dense, like cement. And as they flow downhill, they essentially destroy everything in its path. And there is the example in Colombia in 1985 where 25,000 people were killed instantly from one of these flame volcanoes. The sides of volcanoes as well, they're often quite unstable. This is because they're filled with cracks, because there's a lot of pressure building up on the side of the volcano, so they're riddled with cracks. They're also, in some volcanoes, the material is built up quite quickly, so that slope isn't necessarily stable. So they're prone to collapsing. So from these really big landslides on the side of the volcano, we call this flank collapse. So flank means the side of the volcano. This is Montserrat in the Caribbean, whose flank collapsed. And these are quite worrying for humans because there's been evidence in the past where this has happened. We've had what we call mega tsunamis. So Mauna Loa in Hawaii, so most of Mauna Loa is under the water. So it's got a base about 120 kilometers wide, and it's about 10 kilometers high in total. Only a few thousand pokes out of the top of the water. There's evidence on Mauna Loa of fragments of coral and marine organisms a few hundred meters above current sea level. And they've been dated, etc. And we know it's not from sea level changing that much. And it's thought, and you get loads of tsunami deposits associated with this coral. And there's also evidence underground, we've seen now from sonar, of this giant underwater landslide, which must maybe triggered this incredible tsunami. And there's a concern in the Atlantic, or is it a concern? I don't know. In the Canary Islands, which sit on this side of the Atlantic, they are also volcanic. They're filled with cracks, and a lot of geologists are saying actually this could form an enormous landslide if it does collapse soon, which could essentially wipe out the east coast of the USA if it happened. There was a huge documentary showing, okay, this is going to happen, but as with any geological process, saying it's going to happen now or in 100,000 years, it's hard to say, but it could happen, and if it does, the tsunami will be huge. And tsunamis occur essentially where you have rapid movement, which pushes underwater, which pushes a volume of water very quickly, so it surges. Instead of flowing, it surges in one direction, and that surge eventually meets land and causes a tsunami. Other dangers, so the collapse of an orbital caldera. So where you have a volcano and a magma chamber, once that magma chamber empties, the land above it collapses. And obviously if that happens and there are people around, then that can cause a collapse of the land. And this is rare, it doesn't happen that often, but it can happen. And even just little things like where you have an ash erupted from a volcano and a plane flies through that cloud, that ash gets into the engines, then it can shut them down. And this has happened in the past where a plane flew over an erupting volcano in Alaska, I think it was, around the Aleutian Arc, and it lost all of its engines instantly, but it managed to do an emergency stop. So actually even eruption clouds are dangerous for aeroplanes. And this volcano on the top right, so basically lots of people live on its slopes. It's covered in snow. It's classified as an active volcano. It could erupt at any point. It's going to be very explosive if it does, because it's a felsic or andesitic volcano. Over 100,000 people lay at the bottom of its slopes. So if it erupted, even if people don't get drowned in ash, they could be lahars, they could be landslides. So Mount Rainier in the USA is classified as quite a big volcanic hazard, and it's monitored daily. Just to give an idea of figures in terms of people that have died directly or indirectly from volcanoes, so directly lava, lahars, even indirectly through famine, because people lose their agricultural land. This is a cumulative graph, so after every volcano it increases. So this here is what we think now is the total number of fatalities from volcanoes at present in the last 500 years. So 250,000 people have died as a result of volcanoes. And you can see here there are incredible jumps where we have these massive eruptions. And this is a graph showing the statistics about what they died from. So ash falls, not actually that common. Pyroclastic flows, incredibly common. These things are hazardous, and they can be incredibly hot, and anything in its path will not survive. Lahars, as you can see, it's things like tsunamis, and it's pyroclastic flows, and it's lahars that actually produce most of the fatalities, as well as famine caused by loss of farmland or loss of land, rather than lava flows or gas. Basically, you're only really at a risk of getting killed by lava if you're incredibly close to the volcano. Because even basalt doesn't travel that fast away from the volcano. All these other indirect hazards that are really important. And this is just a diagram summarizing that. Acid rain is another thing as well. When you have a volcanic eruption, or you have a volcano, and you have your sulfuric gases being pumped out, when they mix with, as I said, water droplets, they dissolve and form aerosols. If there's rain in that area, obviously all of that sulfuric acid will come back down to earth, and any plants in the area will die because of this acidic rain. Hot water reaching the surface, if anyone was to fall into a fumarole, they'd die. Less of a chance. But yeah, these landslides, these flank collapse deposits are incredibly dangerous. Pyroclastic flows, ash falls. As you can see, being hit by volcanic bombs is really only restricted to this sort of area. Lava flows. And it can often depend on a tiny factor like prevailing wind. You can predict that this city is actually going to be hit by the eruption cloud, etc., but the wind might change and actually it kills your forest over here. So what do we do? How do we monitor volcanic acids? How do we assess them? So the main thing we do is actually look at the geology. So we look at the deposits formed from previous eruptions. So we can look at whether there are previous lahar deposits. So say we see 10 massive lahar deposits in an area which date back to only 100 years. You can safely say you're in a hazardous area for lahars. Same with lava hazard zones. So this is a map on the bottom right where of Mauna Loa in Hawaii. And the dark purple zones are where there's a large risk of being engulfed by lava, if you like, and then it goes down to a lower risk. And this is all based on looking at historical lava flows and where they flowed, how often they flowed in a certain area. You can build up these maps, and we use zones to assess the risk in that area. And there's always going to be the possibility that a new eruption will form somewhere else. And that's where we use other monitoring techniques. And we also classify volcanoes about how recently they've been active. So this is just the western USA. As you can see, there are lots of volcanoes in the west of the USA. It sits on a plate boundary. This is where we have subduction, not where we have strikes of faults. And there are quite a lot here that have been active in the last 300 years. So just to talk about the Pacific, obviously we sit in a volcanic area, not necessarily on Fiji, it's ex-volcanic, but to give you some examples of particularly hazardous volcanoes in the Pacific. So most of the South Pacific, they're quite young island arcs, but where you have old island arcs, so much thicker crust, much more explosive magma, so Japan has numerous volcanoes that are incredibly explosive. This is Mount Fuji, the most famous. Tokyo lives within 100 kilometers of the volcano. It's erupted 16 times since 781, which is an average of once every 76 years, and it hasn't erupted for 303 years. So people are heavily monitoring this volcano, because if it blows, if it erupts, it's an explosive volcano. The likelihood is you'll have huge ash clouds, you'll have huge pyroclastic flows, you'll have lay loss from the melted snow and any rivers present. Farmland will be affected. This could be a big eruption, and people will have to be evacuated. And another example of a great volcano that I just like saying the name of, Popocatépetl in Mexico. So this is another volcano. It sits on the other side of the Pacific. And Mexico, the cities in Mexico tend to be incredibly populated. So there's a city of 48 million people just sitting 60 kilometers to the east. There's a city of 2 million people 45 kilometers to the west. And we've seen activity in 1922 and 2000, and the activity is getting more aggressive, if you like. So this is another volcano that's heavily monitored, and a lot of people will have to be evacuated if this one erupts. Again, it's explosive lava, it's andesites and rhyolites, so it will be an explosive eruption. So how do we predict volcanic hazards? How do we say something's in danger of erupting soon? Because this is the thing with humans, like a geologist might say, okay, it's going to erupt, it's very likely to erupt in the next 100 years. People aren't going to move for the sake of 100 years. So we have to be quite good if we want to save lots of lives at predicting immediate risk. Obviously it has an element of error, that's why we've had devastating volcanic eruptions in a not too recent past. But basically all of those volcanoes that are classified as active and hazards, we monitor them, and we monitor them quite heavily, more heavily in some countries than others, because they have resources. But what do we monitor them for? So we look at earthquakes, so we use what we call a seismometer, which we'll talk about when we talk about earthquakes. It's a machine that measures ground movement, so it detects earthquakes, sudden ground movement. And often when you have a volcano, when that magma and gas is pushing its way through the volcano before an eruption, there's cracking of the rocks, which causes earthquakes. So quite often before an eruption, you'll see earthquake activity getting more and more and more intense. So if you see that, there's potential for an eruption coming up. So this is an example of a seismic station which is near an active volcano somewhere in the States, I'm not sure where. Other things we can do is monitor gas coming out of the crust near volcanoes, because quite often the composition of gas will change leading up to an eruption. It tends to get, I think, less water and more components of the other things. I'll have to check that, but the composition definitely changes before an eruption, so we can monitor that as well. And if we see that, then we might put an alert on. And we can monitor ground movement, not just from earthquakes, but literally before an eruption, the ground will bulge. It will grow because of the magma building up inside, and it might grow a bit more quickly. It's tells us, okay, we might actually be leading up to eruption. And satellites can help us with that as well. Satellites can very accurately monitor ground movement these days. And actually, we have been quite successful preventing deaths related to volcanoes. So in Mount Pinatubo, see I've given a different year now, it's either 92 or 91, erupted in the Philippines, and actually only a few people died. But it was predicted in the area where they said there was a late harvest, everyone was evacuated. In fact, 250,000 people were in total were evacuated from their homes and their land. And they've gone back and looked at the areas that were destroyed, and yeah, half of those people would have died if they had stayed. But actually, only a few people that died were the people who refused to heed the warnings. So, yeah, we have been quite effective in so many places at predicting volcanic hazards. And just to give you a local example, I mean, South Pacific volcanoes aren't quite as explosive as Japan and the rest of the Pacific Rim. We have older arcs, but there are still volcanic hazards. There's lavas, there's still acid rain, there's still ash being produced from some of these volcanoes. There's still the potential for earthquakes because we have active volcanoes and ground movement. So this is just Vanuatu, the island chain of Vanuatu, a list of all its active volcanoes. And all of these also are lists, so the blue stars are seismic stations. So these are stations that monitor earthquake activity, so rapid ground movement. And as you can see, there are numerous seismic stations around Vanuatu that should pick up on any volcanic, any seismic activity in the area. And they monitor gases as well in certain places. Because a lot of these volcanoes around the South Pacific, if you look down into them, you'll see nice bubbling lava, or you'll see gas being produced. But that doesn't really classify as an eruption per se, that's just background activity. So there's still a potential for a larger eruption. And that's why we want to. And just to give a few examples, this is Hannah. I think the main risks here are just ash fallout and acid rain, which can affect crops and people. But there is a theory that they could, basically an ancient caldera is present and that could collapse, but maybe that's something that won't happen anytime soon. But this is the volcano of Amarin, and this just tells you, for this time and space, this is just advice given, you shouldn't go in the straight line, because essentially it can be dangerous. And just to sum up, there are some benefits. This is our not so happy miner. He looks happy there, miner in Indonesia. If we didn't have sulfur, we wouldn't have matches with various other chemicals. This is where it's mined, volcanoes. They give us heat energy. They give us metallic ores. Remember those hydrothermal fluids? They dissolve minerals. When they cool or depressurize, they precipitate sometimes precious minerals. And they give us nice volcanic soils, so it's not all bad. How are we doing for time? So I'm going to give you a 10-minute introduction to earthquakes as well. I know I'm not, because it's 45 minutes in. Okay, I'll cover earthquakes tomorrow. But this is just to summarize what we've talked today. So volcanoes are not just systems on their own, they interact with the systems on Earth. We've shown that underwater volcanoes actually provide life, like hugely diverse ecosystems, basically feeding off underwater volcanoes. Also the lithosphere, volcanoes produce lithosphere around the crust. They also affect the hydrosphere because they're producing water, and water is interacting with those volcanoes to change the chemistry of oceans and fluids. They release water from the inside of the Earth into the atmosphere. And the atmosphere is altered as well because of all these gases that we produce from volcanoes, and also they can have climatic effects because of aerosols. So predominantly, by far the most lava that's produced on Earth is produced by decompression melting at mid-ocean ridges. That's where most of our lava comes from. As I said, up to 10 cubic kilometers every year is produced by decompression melting at mid-ocean ridges. But most explosive eruptions are found at subduction zones. This is where we have our fluid-induced melting. And volcanoes can cause hazards to humans, but they can also provide benefits. And so the next lecture, I'm going to talk about earthquakes, so I'm not going to start now, but just to give you something to lean on. When I talk about earthquakes, we're talking about the sudden shaking and trembling of the ground caused by a sudden release of energy, generally the fracturing of rocks, or movement of rocks along an existing fault plane in the ground. And they can create some quite devastating effects around the earth. Yeah, I'll talk about that tomorrow.